I think it's a once-in-a-lifetime opportunity as a communication engineer that you have an idea. You start from scratch designing the whole communication infrastructure.
I think that's why we are working here. We want to do the real work. I think as we started, we had no clue that it will take so long.
We were just two guys having an idea, and then the whole journey started. In a research department, you do not have big development projects with 40 or 30 engineers. There are mostly one or two people researching on a very specific topic. We wanted to fix this fading issue, which happens when you are in a large venue and you have your microphone sitting here and then some receive antenna placed here. And then the RF wave is propagated over multi-paths due to reflections. And then you get interference at the receive antenna. So this is the transmitter, this is the receiver, and this interference causes signal fades. This is something you do not want to have on stage. We started thinking about, could it be done totally differently? Can we change it from scratch? Then we came up with the idea to investigate research into broadband technology.
At first, we were not fully clear how narrow these drops are.
Exactly.
And therefore we started some examinations. So we set up a channel sounder to measure the RF channel before we started to develop the whole demonstrator. We went to several venues. We made some outdoor tests, indoor tests, and we tested some large venues, large arenas. And in the end, we even went to Copenhagen to this large shipyard where we had a lot of trouble with narrowband systems.
1.4 gigahertz bicycle tests.
And found out that we can run perfectly in this large area.
Wir kriegen es nicht kaputt.
So I think the main advantage is that multipath transmission is not our enemy anymore.
Exactly.
Now it's our friend. So you can gain from the reflections and you get more out of the signal. And that's the big advantage. And therefore it runs very good in large venues.
How does it work? So this is a very big question. This technology is not new. This is OFDM and TDMA, but it's brand new for the professional audio industry. That you do not a narrowband approach anymore, where just one microphone uses one frequency and transmit continuously, but you use a broadband approach where you use time slots, time division multiplexing, and many technologies from communication systems.
So we're using well-known technologies, but our special problem was to get us to this low latency. Live audio is the main driver for low latency transmissions.
Exactly.
So if you're using in-ear monitoring, you have 2 times latency. So we have a round-trip latency and we wanted to reduce this as much as possible.
Normally, when you have digital signal processing, there's always latency involved. So everything you do in digital domain adds latency to the budget. And you start with a microphone, A to D conversion takes latency, modulation takes latency, transmission takes latency. And here we had to find a very specific solution tailored to this approach that we have an overall round-trip latency of less than 4 milliseconds. Nowadays, you place your microphones like this. You have your frequencies, and then you place microphone by microphone on individual frequencies. And with our approach, we do this totally differently. So each microphone which is transmitting gets the entire bandwidth, but only for a very tiny amount of time. So in our case, this time slot has a duration of 60 microseconds. So this is the idea to achieve these low latencies. And then the next microphone transmits. This is the schema we call TDMA, so time division multiple access. And within this time slot, all the communication takes place, so all the precious audio samples are transmitted.
But the good news is we did not replace frequency planning by time slot planning. The whole time slot planning is done by the system. So in this system we have 11 different modes. It was tailored for different use cases. And due to this TDMA, we are much more free to change audio codecs or change the data rate even for one channel. So by aggregating more or fewer of these time slots, we can run different modes, and it's much easier to provide these different modes. You can decide how to use your frequency spectrum. You can use it all for in-ear monitoring, all for microphones, or mixed up. And now we are able to pack 32 channels in each base station in each direction, so 64 channels all the way, but we need a lot of processing power. And this is really a challenge to get all processors running, to debug them, and to get everything running in each combination. Due to the audio link modes, you have so many edge cases and so many variants how to run this system. This all has to be developed and tested, and that's what we are doing with the whole system.
So the base station itself is just a digital signal processing unit. There are no RF components inside this base station. So it's basically one processor for the whole baseband signal processing, and there are multiple signal processors for audio signal processing. So it's like a number cruncher. It's almost a beast, and I would say it's one of the most complex devices we ever did at Sennheiser.
And by the way, it's integrating a 192-channel sample rate converter just to provide different interfaces. So we have two independent MADI interfaces and an independent Dante, and they can run on different sample rates. Yes. And this is very special as well.
And then we thought, okay, how shall we do all these antenna installations? How shall we support broadcast scenarios where you have studio complexes with lots of RF cables and gain stages and so forth? And then we had the idea, why not use Ethernet and do digital antenna? We have a very good collaboration with our Sennheiser development site in Duisburg. So there are roughly 2/3 of the colleagues sitting in Duisburg.
In collaboration with us, they started to develop the whole hardware. So the PCBs really for the whole devices, the very complex electronic schematics, and to get new ideas from complete different areas. And we're just talking and get new solutions out of this. And this is quite good. Yeah, we had a lot of requirements for the system to make it as good as possible. We need a very powerful software solution to configure all these new possibilities. That was our first reaction. I think this link test software will only be the beginning of this whole ecosystem. So we will add new features to the software, and due to the software-based orientation of the whole system, we are able to add even new features.
What is missing on the desk here now is a handheld transmitter. We need some kind of handheld microphone, which will come soon. It's already under development. And there will be many more ideas we have in the backlog, like an engineering mode where you can tune through various channels as a backline technician and so forth. So many ideas. So when we talk about redundancy, we've asked our customers what are the most common reasons for failures in your field. And we had two answers. First of all, the capsule is obstructed by sweat and makeup. And the other issue is main power supply is just failing. And for both these issues, we had solutions. For example, we equipped the base station with a redundant power supply. Basically, every cable which is connected to the Spectera base station can be laid out as being redundant. So power cables are redundant. We have 4 antennas, we have 2 Dante ports, we have 2 MADI ports, we have 2 power plugs. So every connection is laid out as being redundant.
Yeah, and even today, you only have 1 antenna in your narrowband system, so now you can place up to 4. So it's an advantage for redundancy as well.
And you can decide as operator if you want to use these 4 antennas for range extension or for redundancy.
In the future, we plan a clone mode feature where you can prepare a second base station with your identical setup, and then you can switch in seconds.
So what happens with interference? So each RF device of Spectera, be it a body pack transmitter or a digital antenna, is detecting interference, reporting this to the operator, and even using filter technologies to cope with this interference.
If your laptop fails, the system still keeps running. So you just can replace your laptop, connect it to the base station, and load your show back from the base station, and you are ready to go. It's a very complex system, and As we go to production line, we need very complex tests as well. And therefore, we spend a lot of effort to test each and every PCB, the whole electronics, and the final device again.
Now we changed from a link-based approach to a system-based approach. We have 6 test engineers who build all the test fixtures to do PCB, printed circuit board testing and final testing. And because this whole transmission technology is a proprietary thing, you cannot simply use a Roland Schwartz test system which supports your modulation scheme. You have to design all these test scripts yourself as well. Right now, we bring the system in release 1 as the start of a whole ecosystem. So you can say this is the infrastructure, but this is just the first device out of many. Of course, we will have a handheld transmitter. We are even thinking about further options for belt packs, perhaps in a smaller size. Stay tuned. And we have other ideas, even more in the future. And of course, we are really keen to learn the feedback of the customers, what they need, because we offer a new ecosystem, and I'm totally convinced that there are many ideas from customers. Oh, now we can do bidirectional, so we can use this and that.
But even the handheld microphone will not be only a transmitter. It will lock into the system, and you get full remote control over each handheld microphone as well. So it was a long journey. So I think as we started, we had no clue that it will take so long. But now we are fine.
And at the end, you have the final product in your hands and it's just working. So this is definitely a great journey.